Okay, this is problem number 1 from our test review. Says approximate the area between the function f of x and the x-axis from 1 to 7. Those are my endpoints. Using the left-hand approximation method and 3 subintervals of equal length. And it's multiple choice. We got a little multiple choice. All right, so let's see what we got here. So I've got some graph. I don't really care what it looks like. It is a quadratic, so I mean, it looks like a U, but really what I care about is I've got a horribly drawn number line. Let me try that again. Come on. Thank you. All right, I've got a number line. That's not much better. Okay, so from 1 to 7. So 1, 2, 3, 4, 5, 6, 7. So let's put some numbers here. 2, 3, 4, 5, 6, 7. And I want to break this up into 3 subintervals of equal length. So right here is the start of 1. There's 1, 2, 3. So I broke this up into 3 equal pieces. Now, what I want to do, these are the bottoms of my rectangles. Okay, I want to figure out, we're just approximating the area, so we're using the left-hand method. So to determine how tall our rectangles are going to be, we are going to use the left side of each side of the rectangle. So basically all we're doing is plugging these 3 numbers in to this equation right here. So what I want to do, I want to figure out how tall this rectangle is. So I'm going to plug in the left side of it, 1, into this equation. So let's see, 2 times 1 squared minus 3 times 1 plus 5. What is that? That's going to be what? 2 minus 3 is negative 1 plus 5 is positive 4. So this thing goes up to 4. And there's our first rectangle. Okay. Let's see, let's plug in 3. So 3 squared minus 3 times 3 plus 5. So 3 squared is 9 times 2 is 18 minus 9 is 9 plus 5 is 14. Cool. So this goes up. This is not to scale by any stretch of the imagination. Okay, so this, there we go, like that. Just kind of help us get an idea of what this thing looks like. Probably should have drawn it down here, but that's okay. And finally, for our third subinterval, we're plugging in 5. This is where it's going to get really not to scale, but that's okay. 5 squared is 25 times 2 is 50 minus 15 is 35 plus 5 is 40. So, you know, he goes up there really high to 40. Okay? So now what I want to do, this is, you know, my graph, you know, looks really, you know, it's more of a U shape. That's okay. I want to figure out what the area is under this curve that I've got going here. So I need to figure out the area of each of these rectangles. Well, to find the area of a rectangle, you take the height times the width. So this is a distance of 2 times 4 is 8. This rectangle right here is 8 units in area. This is 2 by 14, so that's 28 units. And this is 2 by 4s, so that's 80 units. So add all those up. 80 plus 28 is 108, plus 8 more is 116. There's our correct answer right there. All right, let's see. Let's get rid of that now. Let's take a look at problem number 2. All right, use the table below to approximate the area between g of x and the x-axis from -2 to 14 using the midpoint. Let's get that midpoint approximation. Whoops, what did I just do? Oh, I'm not in the right layer. Just a second. Time out. There we go. Using the midpoint approximation method and 4 subintervals of equal length. Now, this data is given to us in a table, and I know some people struggle with seeing where those intervals are if you have a table. So once again, let's make, this time we'll give ourselves plenty of room, let's make a number line again. Oh, that is so much better, except for the end. All right, we're going from -2 to 14. So -2, 0, 2, 4, 6, 8, 10, 12, 14, and that's it. We don't have to go to 14. So let me erase, good, I can erase the ugly part. Perfect. Okay, so plan that all along. All right, so here we go. So those are my x values. I need 4 subintervals of equal lengths. This is 1, 2, 3, 4, 5, 6, 7, 8 different intervals here. So if I want 4 subintervals, it means I need to group them in groups of 2. So there's my first subinterval, second, third, and fourth. So these are the bottoms of my rectangles, right? And this time, instead of using the left-hand method, which we used on that last problem, we are using the midpoint method, which means to determine how tall my rectangles are, I'm going to use the middle of that interval. So instead of plugging in -2 or 2, I'm going to plug in 0. So when we plug in 0, look up here. If I plug in 0, I get out 8. So this thing goes up to a value of 8, and there is my rectangle. And in this interval, we'll plug in 4, goes up to 11.5, someplace up here. Once again, I don't care that it's not drawn to scale, it just gives me a picture of what I'm doing. Then we're plugging in 8. Plug in 8, I get out 5. So drop down. Plug in 12, I get out 7.5. There's my rectangles. So now I just have to find the area of each of them and add them up. Let's see, we're going from -2 to 2. That is a span of 4 units. So this is 4 times 8, which is 32. 4 times 11.5 is 46. 4 times 5 is 20. And 4 times 7.5 is 30. And add those all up, we get 30 plus 20 is 50. Plus 46 is 96. That's going to be 98. And 30 more is 128. There is our approximation for the area between our function g and the x-axis from -2 to 14. All right, let's try number 3. Says here, we've got a left Riemann sum, a right Riemann sum, and a trapezoidal sum are used to approximate the value of 0 to 1, okay, so right from here to here, of our function f of x, each using the same number of subintervals. A graph, doesn't tell us how many, it just says the same number. A graph of f of x is shown below. Which of the sums would give an underestimation, that's important, an underestimation of the value of our integral? And circle all that apply. So it could be all of them, could be none of them, we don't know. So let's take a look at the first one, left-hand sum. So let's do this one, we're going to do this one in green. Okay, so if I were to do a left-hand sum, let's just, for kicks and grins, let's just break it into 2 equal pieces. Okay, so 2 subintervals. It doesn't say how many subintervals, so this should hold true for all subintervals, including 2 subintervals. So if I were to use a left-hand sum here, I would use the left side of this interval to determine how tall it is. So this first one is not tall at all. In fact, it's actually at 0. And this one will go up to my function, boom, right there, like so. And we can see that if I were to find the area of these rectangles right here, it is going to be an underestimation of what the actual area is. The actual area is this whole, that half circle or whatever it looks like, quarter circle right there. So this is definitely an underestimation. Okay, let's see what happens when we do a right-hand sum. Let's do 2 subintervals again. Okay, this time we're using the right-hand side, so this time I'll go up here on this side, and this is my rectangle. And I'll go up on this guy, right up to there, and there's my other rectangle. And you'll notice this time that that is definitely overestimating it. So that is an overestimation. All right, then finally, let me erase some of this stuff. Let's try our trapezoid. Erase. Oh, whoops, I can't do that. I forgot, the picture's part of the thing. Okay, so let's see if we can be a little bit more selective about what we erase. I forgot, I'm drawing on the same layer that the actual image of the question's on. So if I erase things, it erases the picture too. Okay, so there we go. So trapezoid sum, once again, subintervals. So trapezoid sum, I just go up on both sides. So that's here at 0. This one comes up here to that point. This one comes up here to that point. And then I just connect the dots. So ding, ding, like so. And there's my trapezoids. Now, kind of hard to tell, but you can see still where that function was right there. This, even if I find the area of those trapezoids, this is still going to be an underestimation. It's going to be a better estimation, but it's still an underestimation of what's going on. So my answer for this one is both 1 and 3. The left sum and the trapezoid sum will give me an underestimation, where the right sum will give me an overestimation. All right, let's take a look at problem number 4. The graph of a function f is shown below. What is the value of the integral from 2 to 8? Now, from the previous three problems, we were dealing with area, or at least I think at least the first two problems we were dealing with area. And with area is always positive, so our answers were always going to be positive. Even if we came up with negative values, well, never mind. We'll see that on one of the extra additional problems with negative values and stuff when we're finding area. This time we're actually trying to find the integral. So values as we go from left to right. So we're starting at 2, it looks like. So we're going to go from here to 8. Okay, we're not doing the whole thing, just from 2 to 8. Values, as we integrate from left to right, values above the x-axis are going to be positive, and values below the x-axis, areas below the x-axis are going to be negative. So keep that in mind. These are nice straight lines, so we can actually figure this out just by, you can count boxes if you really wanted to. But so from right to there, let's see, this is going to be, so this is 4, so this is 2. So this is a distance of 2 by 2, so this is 4 units. Let me erase that plus sign. So this is a positive 4 units right here, and then this little triangle right here, that's 1 by 2, so 1 times 2 is 1/2. So this triangle, 1 by 2, so that's, and then cut in half, so it's 1, let's see, it's a 1, right? I can do math. 1 times 2 is 2, cut in half is positive 1. Sweet. Okay, so now let's come down here. This triangle right here looks to be the exact same size as that one, so this is going to be 1 by 2. Yep. So this is a negative 1 value, this triangle right here. Okay, this triangle right here is, 2 by 2. It's a triangle, so cut that in half. So 2 times 2 is 4, cut in half is 2. So this is a minus 2. So let's see what we got here. We got 4 plus 1 is 5. And then we've got plus a negative 3. And so 5 plus a negative 3 is 2. Correct answer is B. All right, let's take a look at the next one. All right, integrate. Sorry, I got those cut off. Those are 9s right there. Here we go. So if I know for a fact that the integral of g of x from 2 to 4 is equal to 4, and from 4 to 9 is equal to 6, then we need to answer this question, what's happening from 2 to 9. So let's take a look at what this is. So let's say I've got a graph. I don't know what g of x looks like, so we're just going to make something up. So here's 2, here is 4, and there is 9. Okay, and then this, there's my g of x. Okay, it's not drawn to scale. Probably should make it at least a little bit drawn to scale, right? Ish, I don't know. You'll see what I mean by drawn to scale. So this first part, from 2 to 4, so from here to there, the area is 4 units. Okay? Then this guy, from 4 to 9, the area is 6 units. Okay? So now look at this. This thing is asking us from 2 to 9, I've got this. So from 2 to 9, the area is going to be 4 plus 6 is 10. So from 2 to 9, it's 10. So I know that this has to be equal, well, let's take that back, not this, but the integral from 2 to 9 of g of x. Okay, not all this other crap in there. But this has to be equal to 10. That's something that I know. I can glean that from these other two things right here. So now let's take a look at this. Yeah, like I said, I shouldn't have circled that because that's not equal to 10. That would make this problem really easy. But I know that the integral from 2 to 9 is equal to 10. And we'll see how that's helpful in just a second. So do pink. This is fun. All right, so we've got the integral from 2 to 9 of 2 minus 3 g of x dx. Now, rules of integrals. This is a minus sign in here. I can separate these out and treat this as two separate integrals. So 2 to 9 of 2 dx plus the integral of 2 to 9 of negative 3 g of x dx. I can even go a little bit further. I can pull this negative 3. It's a constant. I can actually pull it out, which I'm going to do. I'm going to pull that negative 3 out. So this is going to become a negative 3 on the outside here. So negative 3 times the integral of 2 to 9 of g of x. Okay. Now, look at that. There's where this comes in handy. Right there. Ding, 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 ding. That, the integral from 2 to 9 of g of x, is equal to 10. So what I've got here is I've got the integral from 2 to 9 of 2 dx minus 3 times this, which is 10. Now the only trick is to figure out what this is equal to. Well, this isn't too bad. We can just do the, take the antiderivative and evaluate it. It's a definite integral. So I'm going to come back up here. So we've got the antiderivative of 2 with respect to x is 2x evaluated from 2 to 9, okay? And then take whatever answer I get there and subtract 3 times 10, so subtract 30. So I've got plug in 9, so 2 times 9, minus what happens when I plug in the lower bound, and then minus 30. So we've got 18, subtract 4 minus 30. 18 minus 4 is 14, and 14 minus 30 is negative 16. So there's our answer. This equation right here is actually equal to negative 16, and I find that I eventually have to figure this out, and that's what this information gives us, is how to figure that out. So answer is negative 16. All right, number 6. Which of the following definite integrals has the same value as, oops, sorry, I copied my grammar mistake from Word. This is a 0 to 3. So we've got 0 to 3, 6x e to the x squared dx. So which of the following definite integrals has the same value as this does? Well, let's look at all of our answers and notice what they all have in common, or at least what's different from this. This differential, this integral is with respect to x. All of these are with respect to some variable called u. So it looks like what they've done here is they have tried to solve this using u substitution and then just stopped before they actually took the integral. So let's do that. Let's use u substitution on this and see what happens. So looking at this, our candidate for u, I want to find some part of this function whose derivative is also someplace in here, or at least a multiple of the derivative. And here we go. Look at this. If I take the derivative of x squared, I get 2x, which is a multiple of 6x, or 6x is a multiple of that. So let's do this. Let's say u is equal to x squared. Take the derivative of this, so du over dx is equal to 2x. Separate our variables. Don't have any u's, so that's nice. Equals 2x dx. Now I look to substitute this in. Now I don't have a 2, but I do have a 6. So an easy way to fix that, I could either divide both sides by 2 and not worry about the 6, or I can multiply both sides by 3, and that gives me my 6. Now I can do substitution. So I've got the integral of, I can get rid of 6x dx and replace it with 3 du. So 3 e to the u du. So now I've substituted all that in. Last thing that remains though, remember this and this, these are x values. And I need them to be u values. So we're going to plug these back into our equation that compares u with x, or relation between u and x. So we plug these in for x. So our new upper bound, so we'll say the new upper bound, I plugged 3 in. 3 squared is 9, so my new upper bound is 9. Plug 0 in, 0 squared is 0. My new lower bound is 0. So we're going from 0 to 9. Now let's see if that matches anything up here. Well, I know my bounds are 0 to 9, so that one's not right. That one could be, that one could be, that one's not right, and that one's not right. So let's take a look at these two right here. This one's got a 3 on the outside. That is something that we can do with constants. I can pull that 3 and put it on the outside. So B is going to be our correct answer. That's got a 6 on the outside. So B is our final answer. This will have the exact same value as this does. We've just, all that's happened is we have changed the variable from x to some other variable, in this case u. All right, gosh, that's kind of small. Should have blown these up. Oh well. So this is a definite integral because it's got bounds. So let me rewrite it so it's a little bit bigger. So -2, -1, t subtract. Now look at this guy right here. I don't like having exponents in the denominator, so let's change that to be a negative exponent. There we go. It will help with the integration process. So I'm going to integrate, or take the antiderivative of both. These are separated by a minus sign, so I can take the antiderivative of these separately from each other. Antiderivative of t is going to be 1/2 t squared. And I can check that by taking the derivative, and I still get that. Antiderivative of this, remember I'm adding 1, so this is going to be t to the negative 1, and in order to have a negative 1 out there, I needed to start out with a positive 1. Now if I take a derivative of this, bring the negative down, I get that negative 1, I subtract 1, I get negative 2. So there's our answer. I don't need the plus c because it is a definite integral. You can put it, it's just going to end up going away. Okay. Those are my bounds. So let's see, we got 1/2 negative 1 squared plus, and if you like to, it's actually easier to evaluate, I think, if you put them on the bottom. Whoops, that's going to be it. So this is 1 over t, right? So let me get rid of that t and replace it with negative 1. Whoops. Negative 1 squared is positive 1 times 1/2 is 1/2 minus 1. 1/2 subtract a whole is negative 1/2. Then I also need to plug in negative 2. I need to subtract whatever I get when I plug in negative 2. So I've got 1/2 negative 2 squared plus 1 over a negative 2 to the first power. It just doesn't do anything. Negative 2 squared is 4. 4 times 1/2 is 2 minus 1/2. So this is 4/2 minus 1/2 is 3/2. So I am subtracting 3/2. 1/2 minus 3/2 is negative 4/2, which is negative 2. All right. Problem 8. Once again, a definite integral. Let's do it again. Negative 2, 4. This is 6x squared x cubed plus 8 squared. Okay, now on that last problem, I just looked at it and I could tell right away what the antiderivatives were of both of those terms. This one, a little bit trickier. I do not know what the antiderivative of this is, so we need to use u substitution. Okay, so we're going to use u substitution on this. So once again, I want to see if I can find the derivative of something in here. If I look at this, the derivative of this is going to be 3x squared, and that's going to be 0, which is a multiple of this. So that we're going to set u equal to x cubed plus 8. Take the derivative of both sides with respect to x. This gives me 3x squared, and that goes to 0. Okay. I've got 6x. Well, if I move the dx over, you can see this a little bit easier. I've got this 3x squared dx that I can replace with du, but I don't have 3x squared dx. I've got 6x squared dx, or just x squared dx if I didn't want to worry about the 6. So I want to get rid of the 6 while I'm at it. So I'm just going to multiply both sides by 2. And now I can get rid of this 6x dx, 6x squared dx, and replace it with 2 du. Now, with definite integrals and u substitution, I also have to change the bounds because these are x values. Everything in this equation is with x. I need my new equation, then I'm going to write over here, everything needs to be in terms of u. That includes the bounds. So this is how my u and my x are related to each other. So these are x values. If I want to turn them into u values, I just plug them into this equation. So my new upper bound, I'm going to plug 4 into this. 4 cubed is 64. I think, yeah, 64, plus 8 is 72. My new upper bound is 72. And then my new lower bound, plug in negative 2. Negative 2 cubed is negative 8, plus 8 is 0. I love that. All right, so my new lower bound is 0. My new upper bound is 72. I can get rid of those and replace them with 2 du. And I get rid of this by replacing it with u. So I've got this u squared. And now I'm to an equation that is much simpler to evaluate or take the antiderivative of than this was. So I do the antiderivative of this. This is going to be 2/3 u to the third power. And at this moment in time, I'm starting to wonder if I made a mistake because this is going to be huge. Oh, I think this is the right answer. 0.72. And so I plug 72 in, so I get 2/3 72 cubed minus 2/3 plug 0 in. That just goes to 0. So our answer is this, and I would just leave it as that because that 72 cubed is going to be a very large number. Okay, but I mean, if you did figure it out, let's see, it's going to be divided by 3. It is 248,832. That's what would happen if you typed into your calculator. All right, let's move on. Question 9. Okay, this is an indefinite integral. There are no bounds. Okay. Blow this up a little bit. So we've got secant squared of x minus sine of x dx. All right, so now just looking at this, I can take them separately. I know the antiderivatives of both of these, at least I should. So I don't need to worry about u substitution. U substitution is just to help us when we don't know what the antiderivatives are. But in this case I do. Antiderivative of secant squared is tangent, and antiderivative of negative sine is positive cosine. So there's our antiderivative of this. This is an indefinite integral, so we do have to remember the plus c. There you go. There's your answer right there. Easy peasy. All right, so another indefinite integral. This one, whoops. Oh, I need to get on the layer. There we go. This one, however, when I look at it, x cubed over 1 plus x to the fourth. When I first look at this thing, I have no idea what the antiderivative of this is. So it means we're going to be using u substitution. And if we look at this, the inside right here, the derivative of that is going to be 4x cubed, which is a multiple of that. So there's where we're going to set u equal to 1 plus x to the fourth. All right, so let's take our derivative of that. It gives us 4x cubed. Separate variables, so I get 4x cubed dx. I have an x cubed dx right there, but it doesn't have a 4, so let's get rid of the 4. We'll divide both sides by 4, or times by 1/2, however you want to look at it. I don't need to worry about changing bounds because I don't have any, so this is great. So now we just do u substitution. So here we go. My new integral, don't need bounds, is I've got that stuff right there just gets replaced with 1/4 du. And then I've got 1 over the square root of u, which, let's change that up a little bit. I'm going to, we got 1/4 u to the negative 1/2. There we go. So now this is, I can take the antiderivative of that, a lot easier. So it's going to be u to the positive 1/2 times the reciprocal of my new exponent, so that's going to be 2. Times what I had out in front to begin with, so 1/4, and then don't forget the plus c. So I've got 2/4, so that's it's going to be 1/2 u to the 1/2 power plus c. Now I started with x's, and so when I'm finding the antiderivative of this, I need to end with x's. So I actually have to replace this u with how it was related to x. So the final answer is going to be 1/2 1 plus x to the fourth to the 1/2 power, or if you want to put that as a square root, that's fine too, plus c. And there's our answer. Okay, question 11 says, if f is the function given by this, then what is the derivative of f at 2? So all we're doing, notice this is what f is. So f is the integral from 2x, 4 to 2x, square root of t squared minus t dt, and it wants us to take the derivative of this with f is x with respect to x. All right, so we're taking the derivative of an integral. Now, if you recall, if I was taking the derivative of an indefinite integral, say something like this, okay, then the derivative and the integral just cancel each other out, and my answer would just be t. Okay, if I was taking the derivative of a definite integral, where I have numerical bounds, okay, when I evaluate this is just going to be a number, and when I take the derivative of that, it's going to be equal to 0. So remember, taking the derivative of integrals is kind of pointless usually, unless we have variables in our bounds. Then there's a sneaky way of doing this. Instead of finding the antiderivative of this and evaluating it here, and then taking the derivative, the shortcut was this. I can just take my bounds and plug them in for my variable down here, so for t, okay? So I've got the square root of 2x squared minus 2x, okay? So that's my top bound plugged in, and I just have to times it by the derivative of my bound. So derivative of 2x is 2. And then I have to do the same thing with the bottom one, so minus. So minus, plug in the bottom one, square root of 4 squared minus 4 times the derivative of 4, which is 0. So this whole thing goes away, and that right there is my answer. And let's see, it looks kind of ugly. Oh, we got to evaluate it too. Haha. I'm like, it doesn't look like any of those. Okay, so this is my answer right here. I just need to evaluate it now at an x value of 2. So let's do that. So I've got the square root of 2 times 2 squared minus 2 times 2. All of that times by 2. Okay, so 2 times 2 is 4. 4 squared is 16. Minus 4. 16 times 4 is 12. They go further than that. Oh, 2 square roots of 12. There you go right there. Okay, so that's just a little thing you remember with this. It's the second part of the fundamental theorem of calculus, or the second fundamental theorem of calculus, is when you're taking the derivative of an integral. If it's an indefinite integral, it's just equal to whatever the integrand is. If it's a definite integral with constant bounds, it's just equal to 0. If it has a variable as a bound, all you do is plug the bound into your integrand, like we did right here, and then times it by the derivative of your bound. We have to do that for both of them. Keeping in mind, it's the same thing we do when we evaluate definite integrals. You plug the top bound in minus plugging the bottom bound. Okay, so if these had been reversed, I would have made sure that I had a negative there. Okay, which I believe is an issue with one of the extra problems at the end. Okay, problem 12. It says, find f of x if we know that f prime of x is equal to 2x minus 5, and we know that if we plug 2 in for f, our original function f, we get out negative 6. So we're finding the antiderivative. We want to find f, the antiderivative of f prime of x. So let's take the antiderivative of both sides. Okay, antiderivative of this is f of x, and the antiderivative of this is x squared minus 5x plus c. There is the general solution, okay, to this differential equation, okay. But we can find the particular, or the specific solution, which is what we're looking for here, because I know something about my original function. I know if I plug in 2, so if I plug in 2 into this for x, I have to get out negative 6. And then we can solve for c. So we got negative 6 is equal to 4 minus 10 plus c. 4 minus 10 is negative 6. So my c value must just be 0. So the particular solution for f, in this case, is x squared minus 5x plus 0, which doesn't do anything. So there is my particular solution. All right, 13. Okay, same exact question, just worded a little bit differently. What is the particular solution to the differential equation dy over dx equals x times the square root of y? Given that, if I have my original equation, if I plug negative 1 into it, I should get an answer out of 25/16. Okay, so first, let's find our original equation y. We need to what's called separate the variable. So anything with an x, I want on the right. Anything with a y, I want on the left. So I need to divide both sides by the square root of y and times both sides by dx. All right, so now we're going to take the integral of both sides. This side with respect to y, this side with respect to x. I'm going to change this around just really quick. So I've got y to the negative 1/2 power, okay, and integral x dx. Okay, so antiderivative of this is going to be y to the positive 1/2 power times the reciprocal of that, which is 2. And you can double check your work, take the derivative of this, bring the 1/2 down, that changes to a 1, lower that by a full whole value, goes down to negative 1. Technically plus c, but we'll save the plus c for the other side. Antiderivative of this is going to be x squared times the reciprocal of my new exponent, so 1/2 plus c. Okay, so this is the beginnings of our original equation, our general solution. I do want at this point to figure out what my c value is, and I'm going to use this information to do it. I know that if I plug negative 1 in for x, I have to get out 25/16 for y. So, just draw the line. That was a horrible line. It's kind of hard to draw straight lines. That's better. All right, so I know I have to get out 25/16. So that's my y value when I plug in a -1 for x. Now let's solve for c. So 25/16 raised to the 1/2 power, that's lovely because this is taking the square root. And if I have a fraction, I can take the square root of the numerator and the denominator separately. So I have 2 times square root of 25 is 5, and square root of 16 is 4. Let's come over here, figure out this side. -1 squared is +1, so this is just 1/2 plus c. Times this by 2, so that gives us 2 times 5 is 10. 10/4 is the same thing as 5/2 equals 1/2 plus c. Subtract 1/2 from both sides, and I get 4/2 is equal to c, or 2 is equal to c. So I know my c value is 2. So at this point right here, I'm going to say 2 y to the 1/2 equals 1/2 x squared plus 2. Now we just have to get y by itself. So I'm going to multiply everything by 2. Oh, sorry, divide by 2. Excuse me, divide by 2. So this becomes 1/4 x squared. And that just becomes a +1. And then I can get rid of the 1/2 by squaring everything. So I have y equals, and if you want to square each of these separately or just do this, 1/4 x squared plus 1 square. Actually, you have to do it this way. You can't square those separately. There's your answer right there. The reason why you can't do it separately is because when you square this, it's 1/4 x squared plus 1. It's the whole side squared when you raise both sides squared like that. And if you multiply this out, it is different than just taking the square of that and the square of that. So squaring that and squaring that. Anyways, this is our particular solution. This is what my original equation y would have had to been, given that this is true and that is true. All right, this is the last problem on the actual part of the review. And then there's the additional problems at the end. This one says a particle moves along the x-axis so that any time t greater than 0, its velocity is given by v of t equals 2 minus 9t squared. Okay, so let's kind of envision what's happening here. So I've got a sort of perfectly drawn x-axis. Okay, so this is my x-axis. Okay, and let's see, the particle is at position 4. So let's come here, 0, 1, 2, 3, 4. So to begin with, at time t equals 1, not to begin with, but at time t equals 1, my little particle, and then we're going to use the little center of this little target thing, whatever you want to call it, as our particle. So imagine our little particle guy is right here at 4, so he's just moving up and down the x-axis. His velocity changes. If he's moving this way, his velocity is positive. If he's moving this way, his velocity is negative. And this equation right here is telling us how that velocity is working. So let's see. I want to know what the position of the particle is. So what we need to do is we need to figure out how much does his position change by. And the way we figure out that is by taking the integral of our velocity function. This will get me the net change of his position. So take the antiderivative of that. That's going to be 2 t squared, let's see, times a half. So it's going to be 1 t squared. I'm so silly. I have somebody sitting next to me now. Nathan has joined me, and now I'm a little nervous. Now that I have an audience. Okay, sorry. The antiderivative of 2 is 2t. There we go. And this is going to be what? Minus 3t cubed is going to be the antiderivative of that. All right, so now plus c. Okay. So this is my position equation. So equals position. It's my general position equation. Okay. I know for a fact, it says here, I know that at time t equals 1, that's my t value, I have to be at a position of 4. So let's figure out what c value is. So t, I plug in 1, and I have to be at a position of 4. So 2 times 1 is 2, 1 cubed is 1, minus 3 plus c is 4. 2 minus 3 is negative 1, plus c is 4. Add 1 to both sides, and we get c is equal to 5. So our position equation for this particle, it will tell me the position at any time I want. 2t minus 3t cubed plus 5. That is our, we'll just call it p of t, our position equation. Okay, so and I got that based off of the velocity equation. Now it says the actual question is asking what is the position of the particle at time t equals 2. Well, this equation now will tell me the position at any time I want, and I want to know what's happening at 2. So we just have to evaluate it at 2. What is happening at 2? So I've got 2 times 2 is 4. 2 cubed is 8 minus times of 3 is negative 24 plus 5. So I get negative 20 plus 5. And my particle at time t equals 2 is at negative 15. So it's moving pretty darn quick. If you think about it, from time t equals 1, it was right here. At time t equals 2, according to my velocity, it zoomed all the way down there to negative 15 in 1 second. So it's moving pretty quick. But that right there is my answer. Oh, good. I'm like, I hope it's one of the answers. It is. I gotta love that when that happens. Okay, so like at first this problem looks really complicated, but it's like the same thing as the last problem. It's just got a little story to it. We started out with a derivative, right? This could be like our f prime, and we are trying to find the antiderivative. So our position equation would be like f. Okay, so we're just finding the antiderivative of this, and this information right here is tells me information. If I plug in 1, I get out 4. Okay, so it's just one extra step. I now have to use that equation I come up with and plug in 2. But it's very similar to problem number 13. Okay, so that ends the test review. But I did throw on a couple extra problems, so we'll go through those quickly. Because why not, right? I'm already 42 minutes into this video. Might as well make it a little longer. So these are basically duplicates of some of the problems that we've done. Not all of them, but a good chunk of them. So you'll kind of see some resemblances to them. So this is the same as the first problem. So approximate the area between this function and the x-axis from negative 1 to 2. So here's negative 1. 0, 1, and 2. We want using the right-hand method and 3 subintervals. Sweet. So there's our 3 subintervals right there. Okay, so let's plug in. So we're using the right-hand method. So to get this first box, I'm going to use the right-hand side of it to figure out how high my box should be. So I'm going to plug in 0. Plug 0 into this, and I get out negative 2. Right, negative 2x squared minus 4x minus 2. Plug in 0 and I get out negative 2. So it's actually down here. And that's fine. Okay. Plug in 1. That's going to be the right side of my next rectangle. Plug in 1. I get negative 2 minus 4 minus 2. Negative 2 minus 4 is negative 6 minus 8. Once again, it's not drawn to scale and I don't really care. It just kind of helps me see what's going on. Then plug in 2. I've got... I'll actually write this out. 2 squared is 4 times 2 is a negative 8 minus 8 minus 2. So I've got negative 16 minus 2 is negative 18. So it's way down there someplace. Okay. So there's my rectangles. Now I just have to find the area of them. This is 1 times a negative 2, which is negative 2. However, area is always positive. We're not actually finding the integral from negative 1 to 2 of our function f of x. Okay, we are approximating, not the integral, we're approximating the area, so it's going to count as positive values. Okay, even though it's below the x-axis. In fact, this graph, in case you're curious, here's negative 1. Your graph looks like this. Okay, so here's 2 over here. So we're approximating this area, and yes, it is below the x-axis. So if we were dealing with integrals, if I was doing the actual integral, it would be a negative value. But since I'm just trying to figure out what is the area of this shape, area is always positive, so I don't even care that these are negative. So 2 times 1 is 2, 8 times 1 is 8, and 8, that's an 18, right? Yeah. 18 times 1 is 18, so our answer would be 28. That is the approximation for the area between the x-axis and our function. All right, so let's do this one. Use the table below to approximate the area between g of x and the x-axis. from -2 to 14. This should say, okay, I just found a typo, from 5 to 50. I changed these numbers. I forgot to change those numbers. This should say from 5 to 50. That was a typo on my part. Okay, cross that off. Okay, using the trapezoid approximation method in 3 subintervals of equal length. So as we talked about before, it's kind of hard to see your subintervals sometimes from a table. So let's write these out. So I've got 5, 10, 15, 20, 25, 30, 35, 40, 45, and 50. We want 3 subintervals of equal lengths. We're going 1, 2, 3, 4, 5, 6, 7, 8, 9. And 9 split into 3 equal pieces is 3. So here's the beginning of 1. 1, 2. There's the 1, 2, 3, and 3. There are our 3 equal subintervals. And we are using the trapezoid approximation method on this one. All right, so trapezoid means I want to plug in my 2 ends of my interval. So I plug in 5, I get out 2. Plug in 20, and I get out 10. Okay, there is my first trapezoid. We'll come back and find the area of it in a second. Okay, I've already plugged in that side, so I'll plug in 35, and I get out 26. Okay, and I plug in 50, and I get out 34. Once again, not drawn to scale, but that's okay. All right, so now I want to find the area of these trapezoids. Remember, the area of a trapezoid is you take the average of the bases, those are the sides that are parallel to each other, and then you times it by the height, which is the distance between those 2 sides. So it's going to be this length right here. So for this trapezoid right here, I've got my 2 bases. So I've got 2 plus 10, find the average of them, so cut that in half, times the width, which is 3, plus this one, 10 plus 26, divided by 2, times it by 3, plus this trapezoid, 26 plus 34 over 2, multiply it by 3, figure all that out. So 2 plus 10 is 12, divided by 2 is 6, and 6 times 3 is 18. 10 plus 26 is 36, divided by 2 is 18. 18 times 3 is 54. And then 26 plus 34 is 60, divided by 2 is 30, times 3 is 90. So we've got 90 plus 54 is 144, so 162. I think I can math today. 162, I believe, is our answer. And that's the approximation of the area. All right, 17. All right, another one of these. So let's see. I know that if I have the graph of this function, oops, there's another typo. This should be an F. Typos all over the place. It should be an F. I know if I go from -1 all the way to 8, okay, of my function, the value, so the area of that, so I'm looking at this one right here. So from here to there, the area is 7. Okay? Then this one right here is telling me, hey, from -1 to 5, so 5's about right here someplace. Okay? The area from -1 to 5 is only 2. So once again, not drawn to scale. It's just helping me get a picture of what this is equal to. Okay? So that tells me that the integral, this is the one that we're missing right here, the integral from 5 to 8 of our function f is going to be equal, the whole thing's 7, this part's 2, which means that this has to be 5 because these 2 parts have to combine to make the whole part. So this is equal to 5. And that's going to be helpful in figuring out what this is. So let's take a look at that. We've got the integral from 5 to 8 of 4 plus 2 f of x dx. I can treat these separately, so I've got 5 to 8 of 4 plus 2 times 5 to 8 of f of x. Okay. Well, this, we just figured out what that is. It's equal to 5. So I have the integral from 5 to 8 of 4 dx plus 2 times this, which is 5. Okay. I just have to evaluate this. Let's take the antiderivative of that. 4x evaluated from 5 to 8, and then plus 10 whenever we figure that out. So 4 times 8 minus 4 times 5, and then add 10. So we've got 4 times 8 is 32, minus 20, plus 10. So 32 minus 20 is 12, plus 10 is 22. There's our answer. Okay, so this guy right here is equal to 22. All right, this is a definite integral. Whoops. Let's make it a little bit bigger. 1 to 2. And if I look at these, the integrand here, I'm going to change that to a -3 power. Okay, as I look at these, I can find the antiderivative of these both without any help, no u substitution needed. So this is going to be, what, 2t squared. That'll be the antiderivative of that. This is going to get changed to a -2, which means out here I needed a -4. You can check that all with your derivatives and stuff. Plus c, but it's a definite integral, so the plus c is just going to go away anyways. So evaluate it from 1 to 2. Plug 2 in. Minus, what happens when we plug 1 in? Ugh. I didn't like my first parenthesis, and I tried to fix it, and it made it even worse. Okay, 2 squared is 4, times 2 is 8. This is 2 to the -2 power. That's 1 over 2 squared, which is 1/4. Times 4 is -1. Minus, 1 squared is 1, times 2 is 2. This is 1 over 1 squared, which is just 1. So that's just -4. 8 minus 1 is 7. Minus 2 minus 4 is -2. So it's 7 plus 2 is 9. There's our answer. Okay, this one right here, this is another definite integral. However, as I look at this, I don't know what the antiderivative, oh, another typo, that should be a theta. I don't know, I should be making a note of these so I'll let you guys know, oh well, what the antiderivative of this is right off the bat, which means we'll probably want to use substitution. Now, this is kind of tricky because the derivative of cosine is negative sine, which I have here. The derivative of sine is cosine, which I have over here. So it doesn't really matter which one you want to use. However, is going to be, actually it does matter, because if I tried using cosine, I won't be able to substitute this out because it's inside the square root. So it's actually this guy that we do want to set equal to u. So u is equal to sine of theta du over d theta. Derivative of u with respect to theta is cosine of theta. Separate the variables. It's a definite integral, so I need new bounds. So my new upper bound, plug pi into here. So sine of pi, hey, that's 0. Gotta love that. New lower bound, sine at pi halves is 1. So I have the integral from 0 to 1. It's totally fine that the higher number is on top. That's not a problem. So this is going to be 3. I can replace cosine d theta with du. So it's going to be square root of u du. And this, I can take the antiderivative of that a lot easier. So keep in mind this is 3u to the 1/2 power. Okay. So the antiderivative of this is going to be u to the 3/2 power. I already have a 3 out in front. Multiply it by the reciprocal of that. Well, that's nice. 3's go away. So I've got 2u to the 3/2 power evaluated from 1 to 0. So plug 0 in. And that's easy peasy. That's a 0. Plug 1 in. So that goes to 0. The 1 raised to the 3/2 power, that's like taking the square root of 1 and then raising it to the 3rd power. So the square root of 1 is 1. Raised it to the 3rd power is still 1. Times 2 is 2, so it's -2. So our answer is -2. Okay, so you notice how on that we just did the one prior to this was a definite integral without u substitution. This one was a definite integral with u substitution. So you can imagine the next one is going to be, oh, I guess I didn't copy them down. But you'll notice on the test review, that's kind of what happened. It was 2 of each, one with u substitution, one with not. All right, let's see. If f is the function given by this equation right here, then the derivative of that at -1 is equal to what? So we're taking the derivative of an integral. So we're going to use the second fundamental theorem of calculus. So this is 2x cubed and x, 5t cubed dt. And if we're taking the derivative of this, okay, the shortcut is plug the bound in. So 2x cubed to the third power, and then times it by the derivative of the bound, so that's 6x squared, minus, do the same thing at the bottom, 5x cubed times the derivative of the bound, which is just 1. That's easy enough. This is going to be our, the answer to this, but then I want to evaluate it at -1. If you wanted to simplify this, that's fine. I'm just going to plug -1 in because I just don't care. -1 cubed times 6 times a -1 squared minus 5 times a -1 cubed. So here we go. -1 cubed is -1 times 2 is -2 to the third power is -8 and times 5 is -40. -1 squared is +1 times 6 is 6. It's going to be a -1 times 5. -5 is going to be +5. So -40 times 6 is -240. Plus 5 is -235. Piece of cake. 3 problems left. All right, 21. All right, we are trying to find the original function f if I know for a fact that the derivative is this, and I know this is true about function f. Okay, so I know f prime of x is equal to a -4x cubed plus 2x minus 3. I'm just trying to find the original function. So let's take the antiderivative of both sides. This becomes f of x. This is going to become -x to the 4th plus x squared minus 3x plus c. This is the general solution. Right? The derivative of this, no matter what c is, the derivative of this will be that. The particular solution, though, this tells us exactly which one we need. This is going to help us find c. So I will get out -3. So this is going to be equal to -3 when I plug -2 in for x. Now I solve for c. So I've got -3 equals -2 to the 4th power is 16 times a negative is -16. -2 squared is +4. It's about +6 plus c. So -3 equals -16 plus 10. And -3 equals, what is that, -6. So add 6 to both sides, and 3 is equal to c. So our final answer is this, with just a 3 plugged in there. So f of x is equal to -x to the 4th plus x squared minus 3x plus 3. Okay, there's our answer to that one. All right, problem 22. Same idea. What's the particular solution to this differential equation, knowing that that information is true? Okay, so dy over dx is equal to 2xy. Okay, I want to separate my variables. So anything with a y, I want on the left. Anything with an x, I want on the right. So I'm dividing by y. So this is 1 over y dy is equal to 2x dx. Take the integral of both sides. Antiderivative of 1 over y is the natural log of the absolute value of y, plus c, but we'll save it for the other side. Antiderivative of that is x squared plus c. So here we go. Now I want to figure out what my c value is. I know this is true. If I plug 4 in for x, I have to get negative e out for y. So I have the natural log of the absolute value of negative e, that's absolute value sign, sorry, equals 4 squared plus c. Natural log, absolute value of negative e is positive e. Whoops, I can now get rid of those absolute value signs. So it's just positive e. Natural log of e is equal to 16 plus c. Natural log of e is 1. So subtract 16 from both sides, I get negative 15 is my c value. So I have the natural log, absolute value of y, is equal to x squared minus 15. Now I just have to get y by itself. So to get rid of the natural log, I'm going to rewrite this as an exponential function. Keep in mind this is log base e, right? So it should be e to this power is equal to this right here, the absolute value of y. So to get rid of the absolute value, we just have to treat this as either the positive version or the negative version. Equals y. And now we have to decide which version we want. Do we want the positive version or the negative version for the particular solution? We're going to go back up to this and use this again. I need to get out negative e when I plug in 4. So if I plug in 4 here, I get 4 squared is 16. 16 minus 15 is 1. So if I plug in 4, I get plus or minus e to the first power. And I need it to come out as a negative, so I don't want the positive version, I want the negative version. So my answer is negative ex squared minus 15. And last problem, particles, yay. So particle moves along the x-axis so that anytime t greater than 0, the velocity is given by that equation, which I'm pretty sure I did not change. Silly me. Oh well, that's okay. So I want to take the antiderivative of that. So 2 minus 9t squared dt. Okay, so antiderivative of that is going to be 2t minus 3t cubed. Okay, plus c, right? So this is my position equation, my general position equation. Now for this particular particle, where if I plug in 1, I get out 7. Okay, so I'm plugging 1 in for t. I have to get out 7 for x, or my position, right? This will help me find my c value. So I plug in 1 for t. I have to get out 7. All right, so we get 7 equals 2 minus 3 plus c. 2 minus, that's negative 1. So that's 8. 8 is my c value. So my position equation for this particle that will tell me the position at any time I want is this right here. Now, normally that would be our answer because it usually just asks for the position equation, but this one says where is the particle at t equals 2? So I plug in 2, and we'll figure out where this thing was at time equals 2. So I've got 4, 2 cubed is 8 times that, so it's negative 24. Plus 8, so that's a negative 20 plus 8 is negative 12. Okay, so there you go. We are now at negative 12, which, just think about this for a second, makes complete and perfect sense. Think about this. On the first problem that we did, was problem number 14. It was the exact same velocity equation, except here's what the difference was between the problems. We're going to do this in red. On the other problem, I believe I was at x equals 4 at time equals 1. And we were still trying to figure out what was happening at time equals 2. So check this out. It was the same velocity at time equals 4. Let me see what I'm trying to say. Oh, my final answer to the first problem was negative 15. I remember that. It was negative 15. Well, check this out. All I am is 3 units to the right of this. I've moved over 3 units because what's happened here? I've moved over 3 units from where I began. So my beginning place is just changed by 3 units. So everything else is going to be the same. I've just shifted over 3 units. Cool. Done. That was a long video. Merry Christmas. Have a good day.